Okay, welcome back to the afternoon session. So today we have the first in the lecture series from Nina Amini. Nina is at CNRS and she will be giving lectures on quantum trajectories and quantum feedback control.
Yes.
Thanks.
Thank you very much. Thank you very much, the organizer, for organizing such a nice school. I'm happy to be here. And so today I will describe a little bit the tools that we are working on. So first of all, the basic is the open quantum systems. So this is already presented in other lectures. So just to give you a good reference in this regard, so I would like to present the book of the theory of open quantum system from Bauer and Cedric. So as you know, the open quantum system, you have a system which is in interaction with an environment, and the environment is described by the annihilation and creation operators, which are and this is the theory which is very important in quantum measurement theory, especially, and quantum optics. So let me start about talking about indirect measurements, which is in fact you have the system. So you have the probes on the ancilla, so which comes interact with your system, so one by one, and discrete time. If you you can say the discrete time trajectory. So then the idea is to make the system and the probe state entangled. And like this, you can take information from your system state and without perturbing too much your system. And the idea of quantum trajectory is to estimate your state system based on the measurement record up to the time that you want to estimate, right? So this is called in the field of the people from control theory. They are mostly familiar with filtering, and the people in physics and other mathematicians in probability, I can say. So they use the word quantum trajectory. Okay, so what are the different detections that you can consider? This is also presented previously. Especially the Pierre Gilman, he presented two types of detections, so photon counting and homodyne detection. In fact, the idea is in the photon counting, so you want to detect the emission or absence of photon by counting by using the light field, and here the detection type is. In fact, is in discrete time, or it could be in continuous. Also, in fact, there are some precise time that you record your measurement, and this is by this you present a sudden jump to the state of your system, and this is a typical detection that you observe at the left, and here you have. Otherwise, you can. There's other strategies, which is called homodyne detection, and you have instead of detecting the directly, so you present the local oscillator, and you can then measure the quadratures of the light field at the end, or the intensity of the current. And in fact, here you are talking about the diffusive trajectories, so which has like a Brownian motion. You can see there's the limit of the random walk, right? So today I will present different approaches in order to get the diffusive equations. So just one other thing that I would like to say. So in fact, in quantum optics, the people when they work with quantum photon counting. So here you are working with a stochastic differential equation driven by Poisson processes. And in fact, they use the approximation of the Poisson processes, and they consider the limit of the Poisson process to the Brownian motion. And they use, in fact, they obtain the diffusive equation by looking at the limit of the photon counting, right? Okay, so now I will very briefly introduce what are the control objectives and what are the control features of the quantum trajectories. In fact, you can consider different approaches to control quantum trajectories. Why we want to control, first of all? So you have the quantum trajectories, they have some behavior and stochastic behaviors. And if you don't control, so then you cannot use it in technologies, for example. So that's why important to control. You want to achieve, for example, certain objective that you need to control the behavior of your system. In the open loop control, you have when we talk about the control, usually is a control which is introduced in the Hamiltonian, and this is concerned about the drive that you apply to your system, right? And for open loop control, you have the predetermined controls, so which are time variant objects that, and you change your Hamiltonian like this. And what are the problems that usually the people using this strategy are deal with? They study, for example, the controllability of the problem of the system. This means that if you start, for example, from some initial state, is it possible to achieve some fixed target state at final time? And this is called the controllability. And usually this is useful for the optimal control problem when you want to minimize, for example, some cost function and you design a control, which is, so this is easy control to be in practice. However, when you want to compensate the coherence of the system, this is not very robust to the imperfections. That is why here we talk about closed loop control. So my lecture especially is focused on measurement-based feedback control. But just to give you an overview of the other strategies, you can also have a coherent feedback, which is the autonomous feedback. And here, the study shows that these are more useful in compensating decoherence induced by the environment. So here you have the quantum system, and you have some detection, for example, homodyne detection, and you want to estimate that your system state. So this is, we call here a filter, so which corresponds to the base estimation based on our observation of time, for example, t. And here, what is a measurement-based feedback? Feedback, so by the word, it's clear that there is a feedback, right? There is something that you are closing the loop, and you inject some control input u. But here is a measurement-based feedback. This means that based on the measurement, so you design a controller which depends on the estimation of your system state. And also the signal here is from classical nature, it's a classical signal, okay? Typical example, so here for the measurement, so here you have the experiments, the experience done by Cedric's group at École Normale Supérieure in Paris. So Pierre Rouchon, I think he completely explained this in the previous lecture. So here, just briefly talking about this, so you have some Rydberg atoms, so which are two-level atoms, which come one by one. In the first Ramsey zone R1, and then they have some rotation of their phase, and then you have in the cavity, so which is a harmonic oscillator, and they become entangled with the harmonic oscillator state. And the idea is to use this entanglement in order to get information from the atom state in order to know the state of your cavity. And here, so this is the sum of the measurement. So you have two outcomes for measurement, +1 or -1. And based on this measurement, you have the collapse of your state, right? So, and you know the probability of to have the different outcomes. So especially, so in this experiment, I had a chance to work on during my PhD. So we studied how we can stabilize photon number state inside the cavity, and So the idea is to use the measurement-based feedback. So this is you have the control Hamiltonian, so which is a unitary, which is applied in your Markov chain. And you want to, because if you don't measure, so you have some random behavior of your cavity state towards the fixed point of your Markov chains, which are called pointer states. And you want to stabilize one of these states with probability 1. Right? So that was the objective that I worked on, and I will come back to this in the next lecture. You will see how we can use the control theory, especially Lyapunov techniques, to stabilize quantum state. Other examples of measurement-based feedback. So I would like to talk about these two experiments. So the one at the left, so it's about using the measurement-based feedback in order to do a quantum error correction. So the idea is to generate the grid states of oscillator, harmonic oscillators, which are shown very useful in encoding information. And in fact, you encode the information in the lattice points of the grid states. And and this is shown that this is very robust to the noises, so which are to the errors. So a very nice example of implementation in the Michel group that you can look at. And otherwise, you can also talk once again in the context of superconducting circuits, the experiment done in Irfan Sedi's group, so which corresponds to the measurement-based feedback. The first measurement-based feedback in the context of a superconducting circuit, and the objective was to stabilize the Rabi oscillation, so which is also very useful in quantum computation and so on. And okay, so now I will start just very briefly talk about other strategies, because I think usually today is very important to know, because the theory is very open, so there is not too much analytical work in this regard. So because there is no analog of this in classical control. In fact, here you don't have measurement. You don't introduce the perturbation induced by the measurements to your system. However, you want to control your quantum system by putting the system plant in interaction with another quantum system. And here you have the coherent signal. And in fact, instead of using measurement to get information, so you use the coherent field, so which is traveling between these two systems, and like this you can achieve certain objectives. Okay. So here the typical example. So especially this kind of feedback. First of all, it was used by Mabuchi's group, and at the left you can see an example of the quantum error correction in the context of photonic networks. Here we have 5 qubits. You have 3 registers, so which corresponds to the plant, and you have two other qubits which correspond to controller. Here we don't have measurement. We use the coherent field, which is traveling between these qubits, in order to which play the role of the Sandrom readout. And this is useful, very useful, because especially in the context of superconducting circuits, because you add less noise to your system. And also at the right, so you have another example, so which is implemented by Mabuchi's group, and the theory was based by the work of Matt James, Nurdan, and Peterson, who work too much in this strategy, and they proposed some suboptimal solution for this. And he used this strategy in order to compensate the disturbance presented by the noise in your system. And the idea is to have the optical ring resonators, so 2 optical ring resonators, and which are connected by the beam splitters and so on. So, and you can see the it seems easy to be implemented. This I think is more easier than measurement-based feedback. And he showed that it's very useful in order to inject the disturbances which are introduced, for example, by the noise here. And okay, so you want to minimize the power, the output power. You don't want, for example, the noise which is introduced here can go out also. You want to reduce the power of the noise at the output. So this is another example of this kind of feedback. So now I would like to give you some references regarding quantum trajectories and also feedback control. So this is very nicely presented by speakers, especially by Weisman. So you have the work of Davis, for example, and Balofkan. So everyone knows. So he presented the mathematical rigor to the field of estimation of quantum trajectories. So this is called the quantum filtering. And also we should talk about Bachelor's work. So it's we used the concept of continuous measurement, and also previously it was also intuitively this is also used also by the physicists like Dalibard and Castan and Mulmer. So especially as a wave function approach. And also for quantum trajectory, it was used like a simulation, Monte Carlo simulation of the atomic mass equation. And also in quantum optics, we have the work of Michel. So he introduced, in addition, the theory of cascaded open quantum systems. So this is also useful because if you have different the network of quantum systems, what is the theory about quantum trajectory in this? What is your quantum trajectories in this network? And finally, so I would like also to mention the work of the Dieuzy and his co-authors. So about the quantum trajectories for Brownian motion, so then the idea to use the gravity so for spontaneous emission and so on. And in feedback control, so you have the work of Balofkin. So in fact, his work in filtering, it was very useful in order to modelize the theory of control of open quantum systems. And because in classical control, you have filtering a step, and then you use it for control. So if you don't know, if you didn't have such a theory in a quantum system, it was not mathematically possible to present the feedback control with high precision in this field. And also you have the nice work of the Weisman, so it's about a quantum theory of continuous feedback. So you have here you have the Markovian feedback, so which is you use the signal you're feeding back to your system. So you the direct, so the signal output. And later it was the theory of Balofkin. Also, it was used by Doherty and Jacobs and Mabuchi and by Goff. And here you have the first work in measurement-based feedback regarding the quantum state reduction. Later it was analytically improved, and you have the rigorous work here about what is the adapted the tools in order to study the stabilization of feedback control. And regarding the coherent feedback, we should talk about the work of James and Peterson, Nurdan, and also in this nice paper. So you have in fact they used the work of Michel regarding the cascaded open quantum systems, and they developed a nice theory in order to modular theory, in fact, to how you can describe a network of quantum systems if you know the coupling, Hamiltonian, and the scattering of each of them, right? So they present a systematic theory to do that. Okay, so now I will start writing on the board. Okay, so I will present what is an open quantum system. What I want to do now. Is that okay? Okay, try. It's not yeah, I understand. Yeah, it's fine. Just this is it's fine like this. Yeah. So you have the open quantum system. So here I want to present very heuristically what is the cross map in this case. So you have for the Schrödinger equation, everyone knows that the system evolution is described by a unitary. So how you can use this idea, because you can consider the whole system plus environment as an isolated system, so which is described by unitary. Okay, so in fact the idea is to use. So you have your initial state. You suppose that this is a transferized state, so it's OS 0 transfer will be 0. Okay. Can you see, or is it small? Yeah. So you have. So this is you suppose that it's some state like this, and you can ask what is your state rho t at time t. You know what is the unitary, okay? You know the whole system is described by unitary. What is how you can describe your state at time t by using this unitary evolution. So in fact, rho 0 is the whole initial state of your system, and the evolution is described by this, right? Ut rho 0 ut died. So now, if you replace everything, in fact, what is rho s at time t? What is your rho s? So it's the partial trace, right, of the whole system with respect to the mass. So you have. Right. So if you use this and you replace, so what is the partial trace? So I get the basis of the bath, which is, for example, the orthogonal basis mu. So I'll replace this. Okay. So so I can write everything as the sum over mu and nu of some maps, which is k mu nu. That I will say what is this. So you have rho s0. So in fact, corresponds to the element of mu, ut, and nu. Okay, so this is called the cross map. And so then you can describe your state at time t by knowing the unitary at time t and looking at elements mu nu of your unitary and the initial state of your system. So now I want to introduce what is quantum challenge. So you have no selective measurement. So this means that you have we do measurement, but we don't observe the outcome. Okay. So what is the state in this case? So in that case, you have suppose that you have some measurement operator. Sorry. Ah, yeah. Yes, thank you very much. Yeah. That's good. Exactly. So you have some measurement operator mk. So you have mk dash mk, so which is identity. So we have period. And what is the state at time t? So it's given by can be described by the canal phi, which is applied on the state rho 0. And what is phi? So phi in fact is a map from rho 0 to rho t. And it has so it's a trace preserving three properties, linear and completely positive. And you have a theorem. So it is from Cross, 1983. So you can show that a map has a cross map representation. If and only if it can be, if only if it has these three properties. Okay, you have it well. Okay. And this is for the proof. You can look at the nice lecture notes of Michel Wolf. So quantum channels and operations guided. Guided tour. Okay. Okay, so this is usual. So for the people which are familiar with this, so in fact, this is this concern with looking at the Choi representation. So I don't want to enter in this topic. So now I want to. So this is just about it, very briefly about the quantum channels. So now I want to show how you can get the Lindblad equation. Okay, heuristically. Suppose that you don't know any theory about that. So it's a natural idea to get your Lindblad. So you can say that, okay, so I will write the development of my, I wrote rho, suppose that you know rho 0. You can write your the development of your state at time dt by using just the simple Taylor expansion. So you have rho dt, which is rho 0 plus the first derivative of rho at time 0 dt plus some terms in the order of dt square. Okay. So what is the Lindblad? So you know d rho is you are looking at d rho, so which is L rho dt. So whether you don't know this, but you want to find d rho. Okay. So you can see here you have d rho. So so what we can use? You can use that your rho dt. In fact, is a state, so it can be presented by the quantum channels. Okay. So you can write rho dot t as the sum of some k alpha rho 0 k alpha dag, which sums over alpha. And you want to precise what is k alpha, right? So if you know k alpha, you know rho dt, you know rho 0, you can get here d rho, right? So what is the and you have some constraints. So you know that in fact you should have what is my constraint? So you have the sum of k alpha DAG, so which is identity, right? So first of all, so I want to, you can look at the equation. So I want to have this term rho 0. So what is the k0? For example, I take k0, so from alpha 0 to some we don't know. So which is should be k0 should include the identity, right? Because otherwise you cannot take rho 0 here. And also you have some other terms in the order of dt. So I will call this L0 dt. Okay. But you can say that, okay, this is then sufficient. So then I will have this. However, it's not good because if you have only one cross k0, so then it should be necessarily proportional to unitary. So that's why that you can say at least there is another cross map, so k alpha, such that so you need in fact the other map. Otherwise, this should be a proportional to unitary. Okay, so I will use this constraint. So you have identity, so which is k alpha. So it should be k0 DAG plus k alpha DAG. So now I want to relate this k0 to k alpha to get a less variable, right? So you have you can take k0, it depends on L0. So I will take L0. So any operator can be described by Hermitian and anti-Hermitian operator. So you have some h, for example, minus. So I take h here, a minus IH, such that a is Hermitian and h is also Hermitian. Okay. So now so if you use this constraint, so I don't do the calculation, you can do it, it's very easy. So you will get a, so which is minus half of I forgot to say here, sorry, k alpha. So in order to have dt terms, so you need to take k alpha some like L alpha square root of dt, right? So then you use this, so then a here should be minus half the sum of L alpha DAG L alpha. Okay. So then so we are so you get the linear equation. So minus half anti-commutator L alpha DAG L alpha rho 0. So then you have something, so you can say that, so we call this linear. In fact, this is like a generator, infinitesimal generator of the Markov process. Okay, so it's used for the theory of a Markov process. So here, I forgot to say, you get this if you have a Markovian approximation, right? So it is a Markovian. So it means that, so for example, the evolution from if you look at the evolution between T0, T1, and T2, you can say it's going to here is similar to first to do that and then okay. So we use in fact here, for example, that everything is like this, and so you have rho dot, so which is L rho 0. Sorry, rho dot is right that, okay. So then you can say rho t is exponential L rho 0. So this is in fact is a semi-group, the one parameter semi-group. So this is semi-group. So it means that lambda 0 is identity, and you have lambda t, lambda s can be written as lambda t plus s. And if you look at the properties of this, the spectral properties of this Yorsomer group, you can show that this map is never invertible. So which corresponds to which is coherent with the physics that we know that in an open quantum system, the evolution is not invertible, right? Okay, if you don't have questions, so I want to start talking about 3 different approaches, so which are used in the quantum trajectory theory. So first of all, so this comes from physics. So you have the repeated interaction. So I will describe this on the board, and in fact, there are also some mathematical works that they showed rigorously the convergence of this scheme. So now I will explain this, how you can maybe I can write further. The evolution here if you introduce also a measurement in your system, so you have repeated. What is the repeated interaction? So in fact, you want to get the continuous time evolution, okay, by looking at the limit of the discrete time. Because in fact, that's the thing that is very intuitive. So in fact, you have some ancilla, so which becomes an interaction with your system, and then you measure it, right? And you know what is the evolution if you have of the open system. You know what is the effect of the measurement, okay? So this is the 2 things that you know, and you want to get the continuous time evolution by using this. This is a thing that I personally like. So you have, in fact, the discrete time open quantum system. And you suppose that you discretize your time, so at time t, and the interval of your time, the time 1 is tau, for example. So this is t0. Here you have 0, for example, tau, and so on. So at time t, which is n tau. At time t and tau, you have the same ancilla. So it's important that you have a copy of an ancilla. The same ancilla, which becomes in interaction with your system, and you measure it, and you want to describe the evolution by this scheme. Okay. So first, I suppose that my initial state is a rho tensor sigma. Okay. So the state of the system and the state of the ancilla. So I will introduce some notation. So I will also maybe I will keep it here because I will use it later. So you have a map. So from rho to, suppose that the whole unitary can be described. So this is a unitary. So V, so which is applied on this Hilbert space of your system, and the Hilbert space of your bus. And okay, we know this. So the state of the system can be described by mapping, by looking at the partial trace with respect to ancilla of, and you suppose that you initial instance rise of this. Okay. So I will call this map because it's somehow acting on S, so it's called VS. VS lying on rho. And so at time n, so you have rho n. So it's similar that you apply n times this map in your rho 0. Right? So this is the trivial thing. Yes, exactly. Yeah. So at time t, so I will introduce the measurement operator. So at time t and tau, so you have so you measure some observable of the ancilla. So I will call this MY. So Y is the outcome. So you have the sum of MY dash, which is identity. And I've introduced the map. So suppose that you apply this. So the non-normalized state can be described by a map MY. So which is, so we define it by trace. So this is my notation. So the partial trace with respect to ancilla of applying MY. So V rho sigma V dagger MY, right? And the probability to get the measurement result Y, so it's given by a trace of MY, sorry, not MY, this map, right? And then, so what is the conditional state? So conditional state immediately after measurement. So just after measurement. So this is, I will call it, for example, rho hat. So this is MY, so this map, which I apply on rho over PY, right? You can also introduce the conditional state at time n. Suppose that you are at time n, so which is greater than m. What is your conditional state of n knowing m measurement record? So you have, so you know this map. So I will apply n minus m times, and then m times the map m, right? Rho over p of y1 up to ym, right? Okay. So what is this p? So in fact, it's the trace of my. Yes. Okay, sorry. This is good. So here, I will p y1, so ym, so which is a trace of my my1, right? So now you will consider some concrete ancilla, which is typically the two-level system, right? So you have so HA, so which is the Hilbert space is C square. So the basis is 0, 1. And the unitary that I can consider, sorry, not this, the V is exponential minus, I told the Hamiltonian tensor identity of A plus a square root of tau coupling L 1, 0. So it should be Hermitian. So you have minus a squared tau L dagger 1, 0, 1, right? So this is my unitary. Yes.
So for n steps, you're just coupling with the ancilla, right? With the path.
For n step,
so you wrote rho n equals to us to the power n rho 0. So that's n steps. Where you just do that map.
Yes, you have. Suppose that you have the discrete time measurement, so you have time 1 up to n, and then, in fact, no. Here you mean? Yeah, we have the interaction first, and then we measure, right? We measure, yes. But over there at the end, I suppose that you have the interaction with your ancilla, then you measure. Yes, then you measure up to time m, but after time m, you don't you stop, okay, up to time n. You don't do, you have the, we do measurement, but we don't observe the outcome, in fact. Okay, so it's a, yeah, in fact, it's a quantum channel, right? After time m is a quantum channel. You can have the sum of all the possibilities for the measurement. You don't observe the outcome. Yes, yeah, exactly. Yeah. So, but in any case, just this is for our knowledge. This is not important because from there, so I suppose that up to time n, we have interaction, we measure, and so on. Okay, so this is my unitary, so I will consider. And if you suppose that your the interaction time tau is very small, you can approximate this. So we are in two-level system, so you can explicitly write the unitary. So you have is plus some tau k, so in the diagonal. And here I have what I will say what is k. And here you have a square root of tau l and a square root of tau l dagger. Okay. So what is k? Sorry. So k is minus IH minus half L dagger L. That is an effective Hamiltonian, as you know. Okay, this is my unitary. So now we will calculate every maps that I presented previously. You have, in fact, the map VS rho. I can write here, I think. Okay, VS rho is the trace with respect to Nancy law of this. If you do the calculation, so you will get approximately, so this is rho plus tau, L rho, L dagger plus K rho plus rho K dagger, okay? Yes. A is a Hermitian and so is there a problem here? It should be Hermitian. What is the problem? That's fine now. So here, so that's nice. Once again, we get your Lindblad but repeated interaction, right? So you have, so VS rho, so which is a rho plus something like this. So which is rho plus tau L rho, right? So this is your Lindblad, right? So here once again we obtain this result. So now we want to go further. So to see what is the evolution in continuous time when you have the measurement, right? So I will continue. So to do that, so I will consider an observable sigma x, so which is 0, 1, 1, 0. And suppose that you, I look at the eigenvector of this, so which is plus minus, which is half plus minus 1. And your measurement operator, so you have 2 opacity plus 1 or minus 1. So your measurement is plus minus plus minus. So then this is 1 over 2, 1 plus minus 1 plus minus 1. Okay. So now you look at your map that I presented over there. So if you do my, if you remember, I have my, just to the trace of with respect to A of my, V rho sigma V dag my, okay, with respect to the ancilla. So I will calculate this. If you do that, so you have half plus approximately plus minus 1 over 2 square root of 2 L rho plus rho L dag, so which is not normalized, right? You have this. And the probability to get plus minus 1 is just trace of this, so which is a half plus trace of this, so it should be trace of this thing, right? So now I will calculate my conditional state, so rho hat n. So suppose at time n, so I have n observation. So for simplicity, I will call this rho hat n. So you have yn, and you apply n times this map. Y1, yn of rho 0. So if you do this iterative maps, so you will get rho hat n, so which is L, rho hat n minus 1 plus L rho hat n minus 1, 2 plus L rho hat n minus 1 plus rho hat n minus 1 L dagger minus trace of L plus L dag rho hat n minus 1 rho hat n minus 1 minus this sometimes some process that is an innovation process. I will talk about this delta in. So in fact, you need to look at the limit of this delta in. So what is delta in? In fact, delta in is given by the yn, the measurement result at time n minus yn minus 1 minus trace. I will just introduce the notation lambda n minus 1, 2. So which is type yn minus yn minus 1 minus trace with respect to, sorry, the probability. So you have rho hat n minus 1 L plus L dagger, right? And in fact, what is nice, in fact, you have these two random variables, which is if you look at over there, so you have these are 1 or minus 1, and you know also the probability to get 1 or minus 1. And this thing here corresponds to the average of, if you look at the expectation of yn minus yn minus 1, in fact, you have exactly this thing. Okay? So you have some yn minus yn minus 1 minus the average, and this is known if you have some IID variables, so which are centered. This means that the mean is 0 by the central limit theorem. This corresponds. You can show that by doing some appropriate change of probability. I don't think here in detail. You can by very briefly by central limit theorem you can get this is in at time infinity. Infinity converges to dw. Okay. That's very nice. So in fact you get the diffusive equation by just looking at discrete time model and the limits, right? And okay, so this is the stochastic master equation. You can also usually the people, if you want to simulate this, they're looking the Monte Carlo simulation. So this is instead of looking the n times n matrix, you consider a vector of n, and so which is the you can look at also the literature regarding this also Monte Carlo, how can use the wave function in order to simulate the master equation. So which is because master equation in fact is the expectation of this, right? Especially if you have pure state, you initialize at pure state. If the measurement is perfect, and here is I suppose that measurement is perfect, and you stay in pure state, and from this you can approximately get the average of your trajectories. Okay. If you don't have question, I will continue. How many times? So what is the? Okay. It's fine. I can talk very briefly about quantum filtering, and then one of my students, he will come to introduce you some other approach, which comes from Bernardin's work. And just to finish this session. Okay. So in fact, the quantum filtering, which is introduced by Belafkin, so it was is based on the work of Hassan and Partazarati, so which explain the evolution in the Heisenberg picture, okay, of the interaction between your system. This is also current with quantum optics. So you have the input fields, which are annihilation correction operators. You have your system, and you have the input-output. So this is the work of Gardiner and Côte. So you have the input-output relationship, and you can get the output field. And here, the difference is that you are looking at the evolution of your observable of your system instead of the system state rho. And you have some output field. For example, here we're talking about homodyne. So in homodyne, as you know, we measure the quadrature. So you have A plus A dagger, and the output is the applying unitary of this, right, at time t. And if you measure this, so what is the objective of your of the filtering? So this is in classical words. So it's a very developed field of the stochastic filtering. So you want to you have a signal, you measure a signal, and you want to obtain the best estimation of your signal based on the observation process up to that time. So you can show that this is the best estimation, so which achieves the mean least square errors. Okay. And here in this work, this is also, I think, the presentation of Benjamin Wars. Also, you have seen this A, so which is the integration of the quantized field operator and annihilation and correction operators, and L is a coupling, H is the Hamiltonian, and your user is identity. If you look at xt, the evolution of xt, in fact, xt is your observable at time t. So we change our point of view. So we have the observable instead of a state. And you want to obtain the evolution of your observer at time t just by knowing the evolution of the quantum stochastic differential equation. So this is, in fact, this paper provides, here that I mentioned, provides a quantum rule for the when you are dealing with the quantum noise. Okay? So this is not similar to the usual IPhT table. So maybe not to be very broad. So I just write the IPhT table that you have like this. In fact, it's different. So you have the A dagger. So you have these are 0, and the only no 0 is dt here, and the other is 0. However, for example, Wiener process, you know dw is heuristically is dt, right? But here there is an order in, so you have you are dealing with no commutative noise, right? Okay, so I want to. So I suppose that you know this, and you are agree with this work, and you want to write the evolution of your observer at time t. So djtx. So you know what jtx is. So you have djtx, which is dut x. If you apply the ITOR, in fact, you need to look at all of the evolution of unitary and x, all of the terms, I mean, in the product. So you have ut dx ut dag plus other terms, which is ut dx dut dag. But you know the dut, and if you replace this, you get the evolution in the Heisenberg picture. Okay, so you have L, so which is the dual of your Limrad operator, so which is applying on the operator right now. And you have this, and your observation. If you look at the output field, and you have, if you output field, sorry, Y. If you look at the evolution of your Y, so you will get this, so JT L plus L dagger dt plus dA plus dA dagger. So in fact, what is good? So dA plus dA dagger is commutative, and it's exactly the Brownian motion, classical Brownian motion. And so now up to here you know what is JTX at time t. So in order to do filtering, so what is filtering? So the expectation of JTX, knowing the observation process up to time t. Okay? You can do this conditional expectation because your observation process is commutative. So this is called self-no-demolition property. And also your observer X at time t at the future times, it commutes with all of the observation to the in the previous time. Okay, and so that you can do filtering. So this is a work by Belafkin, and also you can for a less heavy reading. So you can look at the nice paper of 100 Matt James and Wooten on introduction to quantum filtering. So I don't want to enter in the theory because it needs, even in the classical case, you need to know what are the tools in the classical filtering first, and then to use the no commutative version, which is introduced here. So then to get your filtering. So your filtering equation is like this. And now, so the question is, what is rho? Because PTX is the expectation of JTX. Knowing YT, so you can take your devolution of rho because you know what is dPTX from here, and so it's sufficient just to write the ito for both sides and to identify the rho. Right? That's it. And if you do that, you get this equation, which is the diffusive equation. So once again, so this approaches you can use and this is very useful. In fact, quantum stochastic calculus is very useful in coherent feedback. In fact, it's good to work in Heisenberg picture. Okay, so now I will ask my PhD student, Nicolas Moussa, who will present Barthes, because from the beginning, he worked on this approach.
Okay, can you hear me? Yes, it's good. So Nina has presented two ways to derive the stochastic master equation, and I will present another manner, more mathematics. So don't hesitate to interrupt me if you have any question. So this is a work done by Barthes around the same time as the work of Belafkin. You should see it as a mathematical modeling, and there are some assumptions that can be discussed, of course, in this presentation. Okay, so to talk about this work, we need first to dig a bit deeper into the world of probability. So first, with Barthes assumptions, we live in a probability space in omega. So omega is the universe, it's a symbol of all the possible outcomes of a measurement. F, a sigma algebra, just see it as it contains all the sequence of possible outcome up to infinity. Sorry. FT, which is a filtration. I will talk about it a little bit after. Q, which is an abstract probability. I prefer to denote it Q because you see, you will see we will make a change of probability to find the true probability of our world, I could say. And WT, which is a Brennan motion under this probability. WT, you can interpret it as the output of a measurement. Okay, so for the filtration. A filtration, so it's a family of sigma algebra, which represent at each time t, in fact, all the information you can gather up to time t. So for example, I have the first sigma algebra in my filtration at 0, and it's included in any filtration, any sigma algebra ft with t1 strictly positive, t1 positive, included in ft2, t2 greater than t1, and so on and so forth, and everything is included in my filtration, in my big sigma algebra F. And it really represents the information you can gather up to time, for example, t1. Okay, so with Berkeley approach, we find the stochastic master equation in 3 steps. First, we begin with the stochastic Schrödinger equation and even Schrödinger equation at the beginning. Then we will derive what is called the linear stochastic master equation, which is really useful in practice. And finally, if we have time, the stochastic master equation. So first, to understand the linear stochastic Schrödinger equation, we can begin with the Schrödinger equation, basically. It's big enough. So we have the Schrödinger equation. I will write it as a mathematician in stochastic calculus. We put the dt here. And we add a noise, which is in fact the output dWt. But if we do that, we modify the Hamiltonian here. In fact, it's not necessarily an Hamiltonian anymore. So I will denote it only K, KT. And it's not Hermitian anymore. It can be whatever we want. We'll see. So this is the first step. And to make it simple, we will assume that K and L are time independent, but it works also if they are time dependent. We just have to think about the good assumptions. So we have this equation, which is in fact almost this one there. We can also, from this equation, we can derive the propagator. Propagator, you know, if you start from a state psi 0, at time t, you're in a state psi t, which you can write as st psi 0, where st is, for example, here, a matrix. And from this equation, we can also find the equation of the propagator, which is exactly the same. Maybe I will try to explain quickly. Tu dois reparler après ou pas? Okay, I will try to explain quickly how from this equation we can find the mean evolution, so the Lindbladian, with Barkili's approach. Because here we have a k times st, and in fact this k, exactly as what Nina has done before, we can write it as minus I times the Hamiltonian plus 1/2 of L dag L. And this has to do with measurements. So we already talked this morning about projective operating POVM, projective operator valued measurement. Here we can define a projective operator valued measurement as well. In fact, if we take an event F is the filtration, the sigma algebra in the filtration at time t, the following, so the expectation with the probability Q, which is our probability, of the indicator function on F time propagator, st dagger times st. So this is a family of POVM. We can demonstrate it with the definition of a POVM. And in fact, it's strange looking like that, but it's not that strange. For instance, if you want to compute the probability to have the event F starting at state psi 0, it is by definition of the POVM psi 0, and I put the POVM psi 0 by linearity. We have that. And here we can recognize, in fact, it's psi t dagger, here psi t. In other words, this is the expectation value of the indicator function of F times the square of the norm of psi t. And this is not so strange because usually in quantum mechanics, when we want to derive the probability of an event, we take the square of the norm of this event. And you can see it as a density of probability, a probability density in some way. So this is a POVM, and this is the explanation of why it is a logical result. Okay, but at the same time, if you remember my definition of the filtration, Ft is included in Ft plus S, or S positive. So F in Ft, I can also say that F is also in Ft plus S. And in the, exactly as here, I can compute the probability. Yes?
Okay. Sorry, two quick questions. The first one is, why do you take what's the meaning of the average over Q? And the second one is, do I understand correctly that an event in this sense is like a set of possible outcomes of a measurement on the ancilla?
Yes.
Is that the idea? Okay.
Yes, up to time t. And it's just the expectation. You can erase the Q if you prefer. Q is the probability. I denote the probability Q because you can have several probability. And I chose to denote it Q because we make a change of probability. And if I denote it P instead of Q, I think it would be even worse. But it's just an expectation. It's a probability linked to the output, WT is the Wiener process. Okay, so F is also in the filtration at time t plus s. And exactly as before, I will have the probability to have F starting in state psi 0, which is the expectation with the probability Q of the indicator function on F times, I forgot to, times the square of the norm of psi t plus s. But this should be the same as this. Because in fact, it doesn't really depend on what's happening between t and t plus s. And in probability, this has a consequence. The stochastic process is a martingale. I won't detail what it is, maybe after you have questions. But this means that this stochastic process is a martingale. And I can also compute using Ito formula the stochastic differential equation of this process. Which is, after computations, this. Remember, this is supposed to be a martingale. So, if you want to have a martingale, you can't have a shift. Otherwise, you will shift as time goes on. So this needs to be 0. In other words, K plus K dagger plus L dagger L is equal to 0. And this implies that there exists an effective Hamiltonian such that K is equal to minus IH effective minus 1/2 of L dag L. Now, if you replace K in our previous equation, you find this, exactly this. Okay. So now we want to find the linear stochastic master equation. We still live in we consider the same probability space for now. Everything is the same. But we want to work with density matrix because we consider only open quantum systems. Again, with Ito formula, you can also compute the stochastic differential equation associated to this process. And it is, after computation, the Lindbladian, as it is always defined, plus this quantity. And this looks almost like the stochastic master equation. We're just missing a term here that will appear after some change of probabilities. Note that ket psi t is just st psi 0, same here. And if instead of ket psi 0 brac psi 0, I put rho 0, I will have exactly the same equation. So if I denote as here sigma t equals to st rho 0 st dag, I have d sigma t equals the Lindbladian of sigma t dt plus this quantity. Which is the linear stochastic master equation. Why it is linear? Because it is linear in sigma t directly. But be careful, because this equation, and same for the linear stochastic Schrödinger equation, it doesn't preserve the trace. So if you want to preserve the trace, you need to find the stochastic differential equation associated to sigma t over the trace of sigma t. And it's the same for the linear stochastic Schrödinger equation. And this won't be linear anymore, but this will preserve the trace, and this will lead to the stochastic master equation. And to finish our work, we just need to make a quick change of probability. So we change our space, meaning that we change the probability from Q. We have now Q tilde. I will say how we find it, and a new Brownian motion associated to this new probability. So BT. And if I denote rho t equal to sigma t over the trace, again, I can use Ito formula, and after computation, I find d rho t equals to, again, the Lindbladian, plus a quantity that we have seen many times this last week. May have been a bit. Yes?
Is the notation of most of the previous W why, for example, in the lecture.
Yes, exactly. Why is that? Talk.
What is the sense of Q? Because why was not a Brownian motion, but the fact that
1 second. Yes?
what is the physical sense of Q?
This is a good question, and I don't think there is a real physical sense to Q.
Because it is a process which transforms Y on a drifted process, which is W.
It is the probability such that Y is a Wiener process.
Exactly. So physically,
Yeah, it doesn't really have a sense. But it's not important because the true probability is Q tilde, not Q. Q is just a mathematical artifact.
yeah, but it's the beginning of your story.
I say there are some assumptions, and yeah, I agree. But this is still useful because the propagator we found, I think I will stop here. The propagator we found is very useful in computation. Okay, so we have this equation with Ito. And here we find exactly dBT, because if we use Girzhanov's theorem, but I won't give details, we have dBT, which is equal to dWt minus the trace. And this also implies that dWt is equal to dBt plus the trace. And as Raphael said, this is exactly the output, dyt. So this is, again, a formula we have seen many times this last week. And, but I will stop here. The probability Q tilde, in fact, it is the probability, the true probability, I would say, of our world. So it is the probability of the quantum trajectory starting from rho 0. So if we start from rho 0, the probability that our quantum trajectory at time t will be in f is just q tilde of f. And we can't write it with q. And I will stop here.
Just if I have 1 minute just to finish my slides, because I was sorry if I can, or just to say that up to here, we suppose that everything is Markovian. So there's the correlation of the environment is assumed negligible with respect to the characteristic time scales of your system. And for just to give you some initial works in this regard, so you can look at the paper, for example, by DSC here also, and two textbooks that I find it very useful to understand. Thank you very much. Yes.
Yeah. So earlier in the this heuristic method to derive master equation.
Yes.
The very first one. So where does exactly Born-Markov approximation come in here?
Where? Sorry?
Born-Markov approximation. Where does it come in exactly?
The Markovian assumption, you mean?
Yeah.
Yeah. So because you suppose that every time the evolution, you can. I suppose I look at this up to time dt and so on. The fact that I can divide my evolution at each time, so this is Markovian. And also, I suppose that, in fact, you can show that lambda t is contractive, the semigroup. However, for Markovian, no Markovian is not necessarily respected. Thank you very much.